Nice, cool. Thanks a lot. Right, so presentation 6, part 2 of 2. So this class should be fairly light. So where we are here, right? We in section 2. We covered VLANs, we covered layer 2 discovery protocols, we covered Ether channel, and then last class we spent basically the whole class talking about spanning tree, specifically rapid PVST plus, which as we discussed was a flavor of spanning tree. So I'll take a few minutes in this class and I'll go over what we discussed last class just to summarize and make sure it's fresh in your head. We'll go through rapid PVST plus and all these things about root ports and root bridges and stuff, just to make sure it's fresh in your head. And today we'll be covering 2.6 and 2.7. So we'll be going a bit deeper into wireless architectures and AP modes. So you already know what an AP is, access point, but there is a lot more depth in it. And for the basic CCNA, Cisco expanded it in this version of the syllabus. So when I did the exam in the last version, they didn't talk about this stuff too much. They mentioned what access point is, and basically that was it. You had to go off on your own and read up about access points and stuff. But I am glad they put more of it into the syllabus now, because I had to learn all of this stuff. So I actually set up a campus-wide Wi-Fi network, basically, at my old job at Airlink, and I had to learn all of these things. So we'll discuss lightweight access points versus thick access points or standalone access points, and the architectures of them. So we mentioned the WLCs before, if you remember, something called wireless LAN controllers. So they basically control the access points. And they're like the brain of the access points. The access points just do the physical stuff, and the WLC is the brain of it. So we're gonna discuss that, and we're gonna discuss the different places you could put the LAN controller and all of these things. And then, we're gonna discuss the infrastructure connections between them. So how do you actually connect your AP to your WLC? Where do you need access ports? Where do you need a trunk port? And then using link aggregation groups. Remember, we talked about aggregation groups. Well, we didn't mention the word lag before. We called it Ether channel. But when you hear the word lag or link aggregation group, think Ether channel or think bonds. So people use these terms interchangeably. As I mentioned, Ether channel is a Cisco proprietary thing. But in the wider scope of things and in real networks where people don't use pure Cisco equipment, you'll see them use lag or bonds a lot more than they'll use Ether channel. So I came out to CCNA knowing it as a Ether channel, and I called it Ether channel for the first year or two because of my CCNA training. But now I call them lags or bonds because other vendors can't use the term Ether channel. So as you get more familiar with the other vendors, you stop using Ether channel more and you start using lag more. But basically it's the same concept, right? So I always stress concepts over, proprietary names and configuration commands, because if you memorize something in Cisco and then you go and in the real world you have to work on, something between a Fortinet kit and a Cisco kit, you can't use the same Cisco commands. You'll need to adapt your knowledge and you'll need to figure out the commands on the Fortinet appliance or on the Juniper appliance or on the Huawei appliance. So that's why I try to push the non-proprietary things and the concepts more than the Cisco specific things. So in this class, we'll be going through these two topics here. So we're going to delve a lot deeper into this whole wireless networking concept. And next week, we'll finish up section 2. So this whole thing was section 2. So by next week, we'll have finished these 3 topics. 1, 2. Sorry, yeah, these are the 2 topics between management access connections for APs and WLCs, and then configuring the components of a wireless LAN access using the GUI only. So this will just be screenshots because I looked everywhere and I couldn't find a free image of WLAN creation, a WLC, basically. I couldn't find a image because this is a super new topic. And Cisco didn't make it available yet. So they have screenshots and they have a lot of things in the textbook. So I just pulled all that data from the textbook and we'll go through it using those screenshots, using the GUI. They don't care for command lines for this. They specifically mentioned the GUI. But anyway, that's next week. So for this week, let's start back with the spanning tree stuff. So I want to go through just everything we covered in the last class, just so that it's fresh in your mind, and just so that you all can ask any questions if you have anything, and then we'll start off with the wireless stuff. Yeah. 1 second. I can't put up the red cursor yet. Only when I go full screen. Right, so right. Red cursor. So last class we introduced. Did that freeze? No, 1 second. Why are you moving so slow? You all seen my screen, right? Moving a bit slow here. Okay, good, good. And you see the cursor? I'll put it on right, so you're supposed to be able to see it. Cool, nice. So last class we discussed spanning tree. So let me go back to the any one of the diagrams. Yeah, so we could use this. So we discussed this loop basically. We said we had 3 big switches. So in an enterprise or by ISP even, maybe a small ISP, you might have 3 big switches. So these might be big catalyst switches, core switches. These are the big half a rack ones that I showed you. And you might want to set up redundant links between them, right? They might be in different cabinets, different rooms, different buildings even. And just to add some layer of resiliency to your network, you might want to run a triangle or a square if you have 4 switches, or a circle. They call that a ring network. And that is great for resiliency, because it means if you have this link going down, or this link going down, or this SFP failing, maybe this interface gives errors, what else could happen? A crimp could be bad. If these are copper cables, you could have a cable crimped poorly. If it's a fiber connector, you could have one of the connectors that are dirty. A lot of things could go wrong with cables, and in the real world, you'll see in any network you work with, a lot of your problems will be with these links. You'll have links flapping, links breaking, links just intermittently going out of nowhere. Our network will be functioning perfectly, and then 8 o'clock in the night, when somebody is using the network for something very important, that is exactly when this link will break, for example. So just to make sure that user A here doesn't see that link breaking and doesn't see any interruption in their service, you might want to do something like this and put a loop in the network. The problem is now at layer 2, there is no concept of a time to live or a timeout on the data. So frames don't have any fields that say, okay, if you pass through 4 switches or 60 switches or 100 switches, drop or die. They don't have a concept of that. Only packets or layer 3 packets have that concept of time to live. So a frame that comes in here from here could theoretically go here and then go there, then come there, or go up there and go there and come there, and it will keep looping incessantly. It will never stop, no matter how many times it's passed through these switches. So we introduced spanning tree to say we want the redundancy, but we don't want this loop. So in normal operations, we want to break the loop somewhere so that these frames don't just loop around this network incessantly and take up a ton of our bandwidth, which would prevent our real services from flowing through this network. So we went through the process, and I told you that the very first thing that needs to happen in the network is the election of this thing called the root bridge. So in every spanning tree domain, so a spanning tree domain is just a section of a network that is running this special spanning tree protocol, right? So in this case, the spanning tree domain is these 3 switches. So we have these 3 switches directly connected to each other using the same VLAN, and we need to elect a root bridge here in this domain. So we elect this root bridge based on the lowest bridge ID. So remember, I told you the bridge ID is comprised of the bridge priority and the MAC address. So by default, all Cisco switches come out with this priority, this special number here, 32768. So that's just something to remember. I'm pretty sure that was a question. I can't remember if I got it in my exam. But it's just a one number to remember. You don't need to remember any of the other numbers. Just this one, 32768. It is standard in Cisco switches. If you don't change this priority to do anything with spanning tree, if you pull a switch out of the box and you wire it up to a spanning tree domain, it will have this priority by default, 32768. So in that case, if all our priorities are equal, then what happens? The election then is broken based on the MAC address. So whichever bridge or whichever switch has the lower MAC address, that switch becomes the root bridge. In this case, you can see we actually played with the priorities. So someone went and changed the priority and set this one to 4096. So in this case, that is here. So the root bridge there was changed to 4096. And then because of that, he became lower than this one, which was 8192, and this one, which was 32768. Obviously, this is the lowest number here. So the guy with the lowest priority won, because the lowest priority is the main tiebreaker in the election. So your bridge ID is made up of your priority and your MAC address. If you really want to influence that election, you don't go changing your MAC address. I mean, it may be possible to spoof it, but really the priority is there to help you influence the elections. So we went through changing that root bridge. So where was the, let me see. Right, so yeah, this was the command I told you. So we go through spanning tree, VLAN, and a VLAN number, which could be anything, any VLAN you have. You just put the number there, and you put your priority. So you see 4096 is a valid number. So you could put 4096 here, and you'll get the result that we just saw there. The well, the alternative is you could select a higher number if you wanted to, but usually people they leave everything as default, and they choose their two or their one or two most robust switches that are least likely to go offline, least likely to have anything happen to them, and they set those with the lowest priority so that they become the root of the whole spanning tree domain. And of course, I mentioned that with the Cisco flavor of spanning tree, they are VLAN aware. So spanning tree has this notion of VLANs, which is why you have this VLAN here. And you could set your root bridge per VLAN now. It doesn't become a root bridge for the entire network. You could set, switch 1 to be the root for VLAN 1, and switch 2 to be the root for VLAN 2. And then switch 1 to be the root for VLAN 3, and switch 2 to be the root for VLAN 4, and keep going like that. To shorten the configurations, you could do a spanning tree VLAN 1 to 10. Instead of 1, then 2, then 3, then 4, you just put a range. So there's a nice shortcut there. You could also do, where was it? Oh, right here. So I didn't have the screenshot here, but I have the command here. So instead of putting your priority as a number, you could just say outright spanning tree VLAN 1 or 2 or 1 to 100, and then root primary. If you have one big switch that you want to be the root for VLAN 1 to 100, spanning tree VLAN 1 to 100, just like this, and then root primary. Let's read the words root primary, and it becomes the primary root for those range of VLANs. I think Ronald cut. You all still hear me? Hopefully. Yeah. Oh, you joined back. Nice. Okay. And then just to have a backup, so if your primary or root switch goes offline for any reason, you want to make sure that something else is there to take up the slack, almost immediately. So you'll most likely set spanning tree VLAN 1 to 100 root secondary on another switch, just to say that if the primary bridge goes offline for any reason, I will become the root bridge. And usually what we do is we take half of our VLANs, so maybe we have 200 VLANs, we put VLAN 1 to 100, and put the primary as switch 1, and put the secondary as switch 2, and then we take spanning tree VLAN 101 to 200, and we put the primary as the other switch and the secondary as the first switch. So we kind of invert them, just so that we get some element of load balancing. So that if a switch goes offline, it only takes off half the VLAN range. You don't want your whole network going offline because one node went offline. That's the whole concept of resiliency. If one thing fails, one part of a network should fail. The whole network shouldn't fail. Right, so that was influencing the root bridge. And then we said, so this, where was this thing? Right, this was a good diagram to show this. So we said after the root bridge is elected, and we know now how the root bridge is elected, spanning tree goes through and it designates or elects all ports into a certain range or a certain name. It gives a name to every port on the network. So you can see it here, or you can see it in the show command. Where was the show command? I think it was at the end. Right here. So you see we did a show spanning tree VLAN 10 on a switch, and we saw this bridge is the root. So we know this switch or this bridge is the root bridge for this spanning tree topology. But we also know that we have two ports participating in this spanning tree algorithm or the spanning tree process, and we know their rules. So we had the designated rule, we had the blocking rule, and we had the root ports as well. And we know that this makes sense because this is the root bridge and it doesn't have any root ports. The root bridge never has root ports, it never has any blocking ports. All of its ports are designated. And then from there, we go down. So where was this? Right. So designated, root. We just verify that from the show command. And then we go through root costs. So what is the shortest path for every other switch in the domain to get to the root? And in this case, this one link is the shortest way to get here. Going through this way will be harder. And in this switch is this case, right? This is the shortest way to get to the root. And those two ports become root ports. Let's say root port, root port. And then lastly, we had these two ports, and we had to figure out whether this one would be a designated port or a blocking port, or whether this one would be a designated port or a blocking port. Both switches aren't going to block. They're going to have a small election between them, and they're going to decide which side is going to block. So remember from the last diagram, this guy had the lower priority. So he will win an election if an election happens again. And in this case, he doesn't want to become the root, but he is using or he's leveraging that lower bridge priority to say that he's going to keep his port as a designated port, DP. And this other port, who unfortunately has the highest priority, is going to lose that election and he's going to have to block his port. So he is blocking his port here, which is why it's blocking, and he has a designated port. And now we have all of the port states in this domain. They also have some temporary states here. So you can just learn this to figure out if Cisco asks you, okay, a port is in the listening state, is it going to receive a BPU? Is it going to receive a regular frame? Or is it not? So just learn off the names of the transitory states and learn whether it processes BPDUs or whether it processes frames. Alright, and then we went through this summary table. So we said we kind of summarized the port states in rapid spanning tree protocol. So besides making it faster and making it reconverge, right? Reconverge is the name there. Reconverge faster. We also cut down some states. So we only had discarding and then learning and forwarding. Instead of disable, blocking, listening, learning, forwarding, we just went discarding and then learning and forwarding. And in the real world, you will see these states by colors. So on a Cisco switch, when you plug in something, you're going to see it turn orange at first. And you'll see it, light up orange at the top of the cable you plug in. You'll see it light up orange and be blinking a little bit. Depending on which flavor of spanning tree you're running. Again, that might stay orange for up to close to a minute, that 50 seconds we talked about, or it may go green in 5 seconds if you're running rapid spanning tree. And just related to that, we mentioned that, where was it? Right, we mentioned that during that orange time or during that listening and learning and discarding time, the ports are dropping frames. If you pull up your terminal and you try to ping something while you see that port turning orange, you'll realize you're not getting any responses because that switch is just dropping frames for that whole period of time. And this could cause some problems. When you learn DHCP, you'll realize that for DHCP to work, your PC needs to collect some messages from that DHCP server. And during that initial time, those ports will block. The discarding port will block those frames for those DHCP messages. So you'll realize that DHCP won't work, and you may not have an IP address even when your port turns green. So we usually use a spanning tree feature called port pass that allows the access ports to immediately transition to a forwarding state. So you plug it in and it will immediately turn green. And this is used to help a lot of those end devices where we never expect a loop to form because it's kind of just wasting time. And it solves a lot of those problems with things like DHCP. Then we also introduced BPDU guard, which is just a safety net. So if you put a port as port fast and you get a BPDU, then clearly you are at risk of forming a loop because you may have another switch connected and you may have actually tried to form a loop with a port fast port. So that port is going to be shut down immediately. Right? So that was just to show you the context here. That was everything we went through in the last class. Root bridges, primary and secondary, and then the port names. So root port, designated port, blocked ports, and then the port states. So we went through the whole list of the different states that the ports go through. And the primary ones are the forwarding and blocking states. And then the benefits of port fast, which is the last thing we covered there. So now on to some wireless stuff. Alright, come here. Right, red pointer. Good. Now let's switch our focus back to wireless networking and wireless local area networks to explore some more advanced Cisco wireless concepts. Remember that our wireless network revolves around the infrastructure component called the access point, or AP. So our whole Wi-Fi network revolves around this thing called an access point. As we discussed before, the access point is basically a wireless bridge that lets us connect client devices over the air back to our wired networks. So the access point is the thing that broadcasts the signal over free space, so over the wireless air, so that we could use our phones and use our laptops without having our actual cable. The access point is what makes that physically possible. However, due to several limitations of the air interface, enterprises often need to deploy multiple access points to cover their campuses properly. So you can't just set up one access point and broadcast a big signal to cover your whole campus. It doesn't work properly. You have legal requirements or anything. You can't up your transmit power past a certain amount, else you might be at risk of certain health conditions and all these things. And it doesn't work properly either, because if you have too many things connected to a single AP, you realize the AP starts to slow down. So whereas in your house you might have 5 people on the Wi-Fi network at the same time, in a campus or in an enterprise you might have 100 people connected to access points, and that access point just needs to do too much at the same time, and you'll notice that your wireless network starts to slow down a lot. So what they do is they deploy multiple access points and let each access point service 5 or 10 people. So engineers then need to decide on a wireless architecture and AP mode to run in their enterprise network. So this whole thing that we're going to talk about today is guidelines to help you deploy multiple access points in a large network. Yeah. So the simplest architecture is called the autonomous AP architecture. In this design, every access point is configured in standalone or FAT mode. This means that every access point broadcasts its own standalone SSID, also called a basic service set or BSS. Every SSID is associated with a particular VLAN, and every standalone AP is configured independently. So when I say access point is configured independently, I mean the access point has the full range of configuration options. So this is basically what you do with your modem at home. You plug into it or you connect it somehow, and you set up your password, your name, your channel, whatever it is, and that access point is managed by itself. You don't configure 2 access points at the same time, just that one. So this mode is the simplest to understand and configure, especially for small deployments. but it has issues with scaling due to the number of bridge VLANs required, difficulty with roaming, issues with RF interference, etc. So in a business, if you start off in a small business with one office, this is perfectly fine. You have one access point in your one office, and it's super easy to configure. You have an IP address on it or a console cable even. You set up your name and your password and everything, and it works fine with one access point. When you need to do two now, you need to maintain two separate access points. So if you need to change your password, you need to change your password on two access points. If you need to change frequencies, you need to change frequencies on two access points and make sure those two don't overlap. If you need to balance your power and try to get people kind of load balanced on the two access points, you need to do all of that manually. So it becomes a lot more challenging to maintain those access points and make sure that everything is synchronized perfectly across them. Yeah. And just a by the way, in most enterprises or companies, you'll have like a staff Wi-Fi network and a guest network, right? Just as a bare minimum. You'll have one staff and one guests. Now, you know about VLANs now. You know how to configure VLANs on a switch, and you know why we need a VLANs. So on the wireless side, every SSID is associated with a VLAN. So for instance, if you have a SSID called company guest, then that company guest Wi-Fi will be linked to VLAN 90 maybe. And then if you have one called company staff, that might be VLAN 91. And this just gets worse as you light up more and more SSIDs or more Wi-Fi names. So you might have, like a corporate guest for your higher level guests. So people, who very important to the business, but you still don't want on your staff. You might have like a CEO Wi-Fi just to make sure that they always get the best coverage and the best speeds. And every new SSID you light up or with every new name requires a different VLAN. So to synchronize this across all of these APs becomes very difficult. You need to remember that these VLANs need to be created and set up properly and named properly and everything. So you can see how it becomes difficult to maintain. Right, so this is just a diagram showing you how the access points tie into the rest of the network, right? Remember, we discussed this nice 3-layer model here with our core switch and the distribution switch and the access switch. So the autonomous APs just connect in to these access layer switches. So we just run a fiber or run a copper cable, and then the APs broadcast out those SSIDs that we know. So, corporate guest, WLAN 100, whatever you want to name it. And then in the autonomous APs, well, with this setup, every AP is configured by itself. And if we want to duplicate these SSIDs across them, we need to log into every single AP and set up exactly the same configuration. So you can already start to see some of the problems here. We need to configure all of these VLANs on all of these switches and all of these APs, and everything needs to be done manually. Now, another wireless architecture that offers improved scalability is called the split MAC architecture. With this design, we split the functions of an AP into two groups, with one group holding the management functions and another group holding the real-time or data functions. This allows us to shift the management functions of all APs back to a central location. This central location is actually a device called a wireless LAN controller, or WLC, which we know about from before. So the WLC then takes care of all management functions that are shared across our APs. So the wireless security, the roaming, the RF management, all of the managerial stuff, the wireless LAN controller will take care of it. And the big advantage of that is that this is one centralized point now. So we could type in our IPs, or we could console into this thing, and we could configure our settings here. And then this wireless LAN controller will push out the management functions to the APs. So the APs don't actually store the management functions in the separate devices. So we configure it in one place, and it's pushed out and configured automatically everywhere else. So if you want to update our password, we just go in one place, change the password, and that's it. We don't need to remember all the APs and all the nooks and crannies in the business to change the password, just one place. So the AP is then free to focus solely on transporting data or performing real-time functions. An AP operating in this mode is called a lightweight or thin AP. So basically the AP does all the physical stuff, but all of the managerial stuff that we used to do and try to tell the AP what to do before, all of that is being done by the wireless LAN controller now. So we are going to just configure our stuff on this wireless LAN controller, and it's going to be pushed out to all of these lightweight APs. Yeah, so you can see how it's much easier there. So this is what it looks like. So we have our, wait for this thing to go. We have our lightweight AP at the bottom there. And we still have our physical cable going up. So the physical connections will look a lot like the same thing. We just have a cloud there to show that, you know, you might have different levels of switches connecting back. And then you have your wireless LAN controller at top. So your wireless LAN controller manages all of your management stuff. So RF management, roaming management, client authentication, security management, quality of service. So all of that is managed in one centralized place, and then all the APs just pull their settings from that. So you see the real-time functions there below. So RF transmit and receive, MAC management, and encryption. So those things are associated with actual data transmission. So physically getting the bits out onto the air, that is what the AP needs to worry about. All the other stuff, all the other management stuff that we used to configure on it, it doesn't need to worry about that anymore. It just pulls that from the wireless LAN controller. And you see this tunnel going up there. So this kind of cylinder there, it shows a tunnel. So that CAPWAP thing, we'll discuss it a bit more. But basically, what we're saying is that because you could have so many different nodes between the access point and the wireless LAN controller, the access point needs to form a tunnel to the wireless LAN controller just so that it has that direct connection to it. So that it can believe that it has that direct connection so that it could continually just get those settings from the wireless LAN controller. All those management functions that we pulled off, it needs this tunnel to talk to the wireless LAN controller and get those settings from it. Yeah? So in order to support this split of functions between the access point and the wireless LAN controller, a tunneling protocol is required across the network. The control and provisioning of wireless access points, or CAPWAP protocol, facilitates this tunneling. With this use of CAPWAP, our access points and wireless LAN controllers can now be on separate VLANs and networks, rather than having to bridge layer 2 networks as before. So this is, I guess, is kind of advanced networking, but let me go back here. So remember I said every Wi-Fi network has to be on a particular VLAN, right? So like a WLAN 100 might be on VLAN 100. So that's the kind of mapping they give you here. WLAN 200 has to be on VLAN 200. So this VLAN needs to be bridged, and it needs to be the same VLAN across this entire network here. So this VLAN 100 has to be the same network as this VLAN 100, same network as this VLAN 100, same network as this VLAN 100. And because all these things connected, it's basically one big layer 2 domain. And as I told you before, when we introduced VLANs, having these big layer 2 domains brings a ton of problems into your network, right? So this access point might be in a branch, you know, across the island, in Chaguaramas maybe, and this one might be in Mayaro, and you just have this big layer 2 domain between them. So as an example, maybe power could go in Mayaro, and because of the reconvergence and all the protocols trying to reconverge and talk to each other and stuff, guys in Chaguaramas might be affected because they're on the exact same network and they don't have any sort of isolation between them. So we usually don't want to stretch layer 2 networks across such a big domain. We usually try to separate or isolate them as much as possible. And with this setup, we can. We don't need to have a physical, the same physical layer 2 network stretched all the way between all these different APs because of this nice tunneling protocol. Yeah? So we don't have to bridge these layer 2 networks and create the same VLANs as we did before. So this is what it looks like when you have more and more APs. So you have one AP here, one AP here, one AP here, one AP here, and they could be on different networks. That's what the cloud here symbolizes. As long as they could somehow talk to this wireless LAN controller, they will be able to negotiate this tunnel, and then the access point and the wireless LAN controller could believe that they're on the same VLAN because of this tunnel. They believe that they have a direct connection, but they don't. They're on very separate networks, and you could have isolation here. So if power goes here, the guys here won't feel it because they have separate tunnels and they have separate physical and logical networks here, which is why this cloud shows that. You don't have the same exact VLAN being bridged all the way there. Yeah? So now, with this centralized wireless architecture, we are able to implement a number of useful functions and features, such as dynamic wireless adjustments for each AP, transmit power optimization for each AP, quick client roaming between APs, centralized security management on APs, and a lot more functions, right? So basically, we don't have to log into each access point by itself and configure passwords or tune down this power and turn up the other power to try and get clients balance between them and make sure you connect to that AP and you connect to that AP, and make sure both of them not using the same channel so they don't interfere with each other. None of those things. The wireless LAN controller configures a lot of those things for us. And there's a lot of intelligence and a lot of current work is going on to put more intelligence into the LAN controller there. So it could dynamically tell you which AP you should be on. It could dynamically adjust transmit power. It could adjust the width of the channel or which channel it's using, all those things. Because it has so much control over the access points. Note that with this architecture, we can place the wireless LAN controller in several areas in our network. We can place the wireless LAN controller near our core switches or routers to ensure that it is simple to share this resource among multiple APs. This is called a unified wireless LAN controller deployment. So we discussed the wireless LAN controller, and now we're going to discuss different places we could put this LAN controller on the network for different reasons. So with the unified wireless LAN controller deployment, with this name of deployment, we put it near our core layer. So we have our APs here, and the AP needs to talk to all of these things and go back to the core layer here. But that will mean that it has a very nice fast connection to this core switch or this core router here, right? Remember, these things are really beefy, and they might have, you know, a 10 gig connection or a 100 gig connection. So all of this traffic could flow easily to this wireless LAN controller because it has so much bandwidth and because these ports will be so big. Now, instead of deploying the wireless LAN controller as a physical device, we can also choose to implement a cloud-based wireless LAN controller. In this model, we simply spin up a VM in a cloud platform and implement our wireless LAN controller image there. These deployments may support a slightly smaller number of APs, but we can deploy multiple VMs in the cloud to compensate for this. So this might be a physical box that we put into a rack, but we could also just buy an appliance and buy a server and put it as a VM on the server. Remember, we discussed hypervisors and all those virtualization things. So this might be what it looks like if it's a cloud version. So this isn't a physical appliance, this is just a server that has a connection into the core layer, and we put an image, just like a Windows image or a Linux image. We install an image for this wireless LAN controller on the server, and it's just, you know, one appliance in the server. It's not a whole physical device. For smaller deployments, we may also choose to deploy embedded wireless LAN controllers, in which the controller is co-located in one of our network switches, or a Cisco Mobility Express wireless LAN controller design, in which the wireless LAN controller is hosted within one of the APs in our network. These designs can typically only support 100 or 200 access points maximum, but this might be fine for smaller enterprises. So rather than going through all the hassle of buying a completely separate box or a separate VM appliance, which will be more money, we could just embed the wireless LAN controller in an AP or in a switch. And Cisco has features and special switches and special APs to support this. So it'll be cheaper because you don't need to buy a separate appliance. You might still have to pay a license, but it'll be cheaper. But of course, everything is a trade-off. And the trade-off here is that you might be able to support as many APs as you might be able to support with the dedicated appliance or with the cloud-based appliance. So these embedded designs might be suitable for smaller places, but not larger places. Yeah. So embedded wireless LAN controller, so you see co-located on the switches here, and then on the access points here. So yeah, there, and there, and there. And the difference will be power and price. So you might expect that this one will be the cheapest because you just buying your access point and you kind of getting a bonus wireless LAN controller with your access point. Whereas with this, you need to buy a switch and you need to pay for a license to embed this wireless LAN controller on the switch. But this one will be more powerful than this, most likely. Now, instead of having to manually configure our wireless LAN controller for our split MAC architecture, there are also a number of cloud-based services available that allow us to simply point our access points to them and utilize a dashboard to manage them afterwards. The cloud service provider manages the wireless LAN controller software and the VM and all the setup. This third wireless architecture type is called the cloud-based AP architecture. One example of this is the Cisco Meraki service. In this architecture, the management and data planes are still split, with the Meraki cloud service managing all of the management functions for the APs. So basically the difference between this and the cloud-based wireless LAN controller from before is that these are sold as software as a service, basically. Just like, think of it like Facebook or Google Drive. It's just a service that you could pay for, and everything behind the scenes is configured for you. So they will just give you like a small setup guide, and they will tell you, hey, when you're setting up your AP, point your access point to this IP. And that's it. Everything with the wireless LAN controller will be managed for you. You just have a nice pretty portal to enter your password and enter how many Wi-Fi networks you want, and everything will be managed for you. You don't need to worry about, a server and setting up a VM and a hypervisor and all these things. Don't worry about that. Just point it towards our service. So that's what this cloud-based AP architecture is speaking about. So you see here, we have all of our physical links going out here, and usually we buy special APs for this. And then all we need is an internet connection going out from our core switch, and somewhere in the cloud, this service is being hosted, and we'll just get a public IP or a URL, and we'll point our APs towards that. So we'll just type in the IP or type in the URL, and the APs will go and talk to that magic server in the cloud, and they will set up their Kappa app tunnels and everything to that cloud service. Yeah. Now, besides the two main modes that APs can be configured in, so we spoke about autonomous versus lightweight, there are also a number of other special purpose modes that a lightweight AP can be configured in. So besides the whole big categories of autonomous APs and then lightweight APs, you also have another bit of special modes that you can put an AP in for certain niche cases. So in local mode, this is the default lightweight mode. It offers one or more SSIDs, and then at idle times, it listens for interference and noise, discover rogue devices, whatever else. So this is the intelligence I was speaking about. So usually access points will be worrying about getting data to and from your phone, but if it's idle, your wireless LAN controller could tell it, listen for some noise, listen for interference, listen for access points that should not be there, and maybe hackers trying to get onto the network or trying to sniff people's traffic. So the wireless LAN controller might find more use for it, but usually it's there transmitting and receiving data. Now you could also put it in monitor mode, where it doesn't transmit, it only listens to detect rogue APs, IDS events, and clients. So this AP is just a special AP that could be deployed to perform these security listening events. It doesn't need to actually transmit and receive data to phones and to laptops and things. We also have Flex Connect APs, which act as a backup to Kappa app tunnels by moving traffic between a VLAN and an SSID. So this might be, if you have a very special access point and a very special SSID, and you don't want that SSID to disappear for any reason. So if a AP dies, or if the plug is pulled on it or something, if you lose power, you could put a Flex Connect access point to say, hey, you become the backup for this. So if this other access point fails, you become the backup. And then you have a sniffer AP, which listens for 802.11 frames on the air and forwards them to a packet analyzer. So if you have a place where you feel somebody might be listening on the network or broadcasting frames they're not supposed to be, you can set up a special sniffer AP that just puts frames into Wireshark for you, and you can see what's on those frames. You also have rogue detector, just specifically for rogue APs, nothing with IDSs or anything. You have bridges, which act as a dedicated bridge to connect two wireless networks and form a mesh network. So if you have a network between two buildings that you want to connect wirelessly, you can set up a wireless bridge, which is a mode that an AP could work in. You have Flex Plus Bridge, so you could combine the function of Flex Connect and Bridge, and then SE Connect, where you perform only RF analysis to analyze, to capture and analyze spectrum or wireless channel data for noise and interference analysis. So we're not too concerned about the security analysis here. This is more for spectrum and wireless noise you want to analyze here. So these are all niche and special modes, and obviously AP is super expensive. So you may not see these being used as much as as much as you think, but they do exist and they are possible. So you might have an AP just to set up as this, just for a week or a few days if you think there is a problem on your network and you need to get this data. You need to capture this sort of special data on your wireless interface. Now that we've examined the core components of a WLAN or Wi-Fi network, as well as some of the architectures that we can arrange our components in, we can now explore the physical connections that are required between these components. Let's first examine how you can connect a Cisco AP. Depending on the particular model, a Cisco AP can have a multitude of ports. So check the particular model for any strange ones you see. So I can't tell you, every AP will look exactly like this because, they always releasing new APs and they all have special ports. But I can give you a basic rundown of the most common APs you'll see. So on most Cisco APs, you'll see a DC power port for powering the AP, a console port for initial configuration of the AP, and one or more Ethernet ports for upstream connectivity to the core network. So power the AP, configure the AP or manage the AP, and then connect the AP to the rest of the network. Basic connectivity. So this is, it's an upside down version because it kind of meant to be upside down, right? So you usually attach the APs to the ceiling, which is why it's so white and plain. It's supposed to blend into the ceiling. And usually you have these adapters or these screws up here, and you'll screw into the ceiling, you'll put a bracket there, and then you'll kind of attach these APs to that bracket. So that if you need to remove the AP for any reason, you can just screw it out, or twist it out, or pull it out from the bracket, and then put it back in. So you can kind of see a rundown of the kind of ports you're expecting. So you're seeing your power here, or your Ethernet connection / PoE connection. So if you can't get a power connection into this, just plug in PoE. You have your aux port, which may be used for bonding or maybe used for a backup connection, like a modem connection. People use a lot of these things for modem. So if you have a 56 kilobit per second modem, like a dial-up modem, and you need an emergency way to access this AP, you just plug in that 56 kilobit modem into this with a telephone line, basically. USB connection for emergency firmware flashes, and the console connection, just to manage our switch or manage our AP in this case. So depending on the capabilities of your switches, you can sometimes utilize PoE to provide both power and data connectivity to APs over a single Ethernet cable. So we discussed PoE already. However, be careful with this. Multiple PoE standards exist. So you have AF, AT, and BT, a bunch of different standards, and they're not compatible with each other. So you could blow up your equipment if you send the wrong amount of power to it, right? So be very careful. Read your manuals and read manuals on both sides. So whatever's supplying the power and whatever taking the power, make sure it's using the same PoE standard before you plug it in. So ensure that your AP and your switch use the same standard. In some APs, you can connect multiple uplink connections to create a link aggregate port, so a bond, to your switch. So the aux port usually supplies this extra physical port. Depending on the AP, it might be the aux port is a backup management port, or it might be the aux port is a second Ethernet port to bond, depending on the AP. So depending on the architecture, you would configure your uplink as a trunk or an access link, depending on the architecture. So you see here, with this autonomous AP, you configure a trunk link. So remember I said you need to really be very careful with those VLANs and those Wi-Fi names with the autonomous AP. So if you set up two SSIDs or Wi-Fi networks, you need to break out those two VLANs on the access point and then make sure those two VLANs created on all the switches on your switch LAN. And I had a ton of problems with this. You need to very carefully manage those VLANs and make sure those VLANs are configured in every single switch in the network, and you can't use those VLANs for anything else. Those things need to be only for these Wi-Fi networks. However, with the lightweight AP, it becomes a lot easier, right? So you just configure access link and use one normal access VLAN and give this AP access to the wireless LAN controller. And then the AP will set up a CAPWAP tunnel to this wireless LAN controller over that one access link, and it will set up all its VLANs and everything over that tunnel. So over your normal physical network, you just need one VLAN. And it doesn't even need to be a special VLAN for these APs or anything. It just needs to be a normal access VLAN that gives it access to this wireless LAN controller. And this is the power of tunneling. So you could put 100 different VLANs to this AP over this tunnel, and this is still one normal access link. You don't need to worry about creating those 100 VLANs in a bunch of different switches in your LAN. Just that one VLAN. Now, connected wireless LAN controllers can be a bit more convoluted. Wireless LAN controllers have several types of ports, which we have to become familiar with. So service ports are one type of port, and these are used for out-of-band management, recovery, and booting functions, etc. This is usually an access port. Then we have distribution system ports, which is used for all data traffic to APs. It requires a trunk link and can utilize lags. So this will be the heavy port, right? This is the port that is actually transmitting all of the traffic that people using over your wireless network. And this is a trunk link, and it can utilize lags. So these are the places we might need bonds, because we want to make sure that we can handle all that capacity and all that traffic. Then we also have console ports, which is used for serial cable management, as we know. And then we have redundancy ports, which is used to connect to other wireless LAN controllers. So this is kind of what it looks like. So you have your console port for management, you have your service port for out-of-band management. So like if you want to SSH into this thing, your service port is how you'll do it. If you want to physically go and plug into it, you plug into it using your console. If you want to actually get traffic to and from your APs and to this wireless LAN controller, you use your distribution ports. Yeah, and of course those kappa tunnels will be set up across those distribution ports. Through the physical distribution ports, we configure multiple logical interfaces on our wireless LAN controllers to map to each VLAN as required on our APs. Thus, each unique SSID on our AP is associated with a unique dynamic interface on the VLAN. So this is what I was mentioning before, right? Each unique SSID or each Wi-Fi network or each Wi-Fi name is associated with a VLAN. And now we're telling you is also associated with a dynamic interface on the wireless LAN controller. These dynamic interfaces on the wireless LAN controller should be configured with private addresses for management as well. So this is what it looks like. So you have your access point, you could have different SSIDs on them. So, company guest, company staff, company CEO, or company C-level exec, whatever it is. You set up different Wi-Fi, WLAN networks for that, and different VLANs for it, and you have a different dynamic interface for each one of them. Yeah, and usually you have different VLANs, different separate sets of VLANs for management, and for redundancy management, and for your service ports. So you usually don't want to put what they call in-band management, which is the same VLAN that you're using to access the internet. You can manage your access point or your wireless LAN controller from there. That's a security risk in most cases. So you usually want to put a different VLAN for that. And that's it. See, today's class would have been nice and short and easy. So it's not too deep technical topics. It's really just concepts. So all we did just now, we went over the rapid PVSC stuff or the span increase stuff, and we discussed these different terms again. And then we went through and we compared Cisco wireless architectures and AP modes, and we went through some different physical connections of the wireless local area network components. So how do you connect up all of these things together? APs, say wireless LAN controllers, where you need access ports, where you need a trunk port, and where you could use lags to increase your capacity and your resilience. So yeah, just a lot of theory, and I hope that wasn't too difficult, because I know the span increase stuff a little heavy. Right, so for today, we'll go through lab 11. So take a try at lab 11 and let me know if you have any problems. And once you're done, that's it. Yep. So you can stop recording and